Here's a worked example from a book problem of a hypothesis test for proportions. Specifically, the one proportion z-test is what we're going to use. It's a question. It's based on a survey about absenteeism in schools. There's a 1996 survey that's used as a baseline for comparison that discovered that 34% of students had not been absent from school during the previous month. And then in 2000, 4 years later, a survey with 8,302 responses gave a figure of 33% for the same question. Do these figures give evidence of a change in student attendance? Okay, so we want to know, the plan is I want to know whether there's been a change in student attendance from 1996 to 2000. Okay, and there's the suggestion that we're going to use the 1996 survey as a baseline. Okay, so we're going to use that number as our reference. In other words, we're going to make the null hypothesis that the percentage is 34%, and that maybe the 33% we're seeing is just random variation. Okay, so the null hypothesis is that the proportion is still actually 34%. Now, this is we can have a more sophisticated approach later where we could actually maybe think about the variability in this figure. But let's assume that this was a survey with an immense number of responses and we're really sure of this number. Okay, if we weren't sure of this number and we thought that had some variation, we would actually use a two proportion z-test, which comes up in a couple of sections. Okay, so in terms of the notation, H naught is the hypothesis that the true proportion is 0.34, and the alternative hypothesis is that the proportion is not equal to 0.34. Now here's where we need to figure out whether we want a one-sided test or a two-sided test. We're asked, do the figures give evidence of a change in student attendance? And we're not specifically saying, oh, well, if attendance went up, we wouldn't care. There's reasons why we might want to study it that way and say, okay, I don't really care if attendance goes up, that's great. But that's not really what's being asked. Is it evidence of a change at all? Who knows? Maybe maybe the true proportion is now 36, and the 33% was a particularly large variation from that 36 true percentage. Okay, so we will use a two-sided test here. Okay, so that's the alternative is really that it's anything different, not just higher or just lower. That's a subtle issue, but here we just want to figure out the two-sided. Okay, so let's look at the assumptions and conditions that we need. Okay, we have the independence assumption. Okay, well, hopefully the absenteeism will assume that each student's absentee record is mostly independent of others. Now there's some issues because absenteeism could be due to sickness, which can come in waves and where there might not be independence. But hopefully that's not a strong effect, especially with such a large number of people who are almost certainly from various different schools. It definitely wouldn't influence each other in any obvious way. Okay, so it's, as usual, it's an approximation, but it's probably pretty good. Okay, randomization. The randomization condition, well, it hasn't told us too much about the survey dynamics, or about the actual mechanism of the survey. We'll assume that the survey was close to a simple random sample. Okay, and that's something that we might want to go back and look. Oh, can you tell us the mechanics of the survey so we can be more sure of this? Okay, the 10% condition. We need to know what the population is. Okay, well, this is a national survey, and so 8302 responses is nowhere near 10% of the total number of students in the country. Okay, so 8302 is definitely less than 10% of all students, so that's good. Okay, and then of course the success-failure condition. To make the math simple, make these normal approximations really good approximations, well, we've got NP. Well, let's do that in math mode. NP is 0.34 times 8302, which is equal to something pretty big, like 2823. Okay, 2823, and NQ is even bigger. It's 0.66 times 8302, because Q is just 1 minus P always. Well, I don't even need to calculate it. It's bigger than 3,000. So these are huge, much bigger than 10. Okay, we hardly We didn't even really need to do that calculation. This is big numbers. Okay, so we've got the basic conditions. And so we are set up to do a one proportion and two-sided z-test. Okay, and so let's do the mechanics of that and find a p-value. Okay, so we need to find the standard deviation of the sample proportion. So remember, this is p hat. We've got hypotheses about the true. That's p is called the true. We could think of that as the real proportion in the population, or just the population in our model. The p hat is what comes out of a sample, and the standard deviation of all. If I look at a bunch of samples and think about how those vary, some would give 33%, some would give 32, 34, 31, 36, whatever. The standard deviation of that is a known fact because we've satisfied the conditions. Okay, so we use the null hypothesis numbers P naught and Q naught for the formula for the standard deviation. That's the nice thing about a hypothesis test, is we've got a lock on what we are going to assume in terms of the null hypothesis true about P. Let's look at the hypothesis that P is 0.34. If that were true, we would actually have a precise estimate of the standard deviation. So that's cool. Okay, so that's going to be the square root of 0.34 times 0.66 over 8302. We'll do that, and it's going to come up in a place that's not convenient, unfortunately. And it's 0.0052. Okay, if we take it out of standard scientific notation. Okay, so what does that mean? Okay, it means we can now calculate the z-value. So we've got a percentage. Our observed p hat is there for the one sample we really did do is 0.33, and we want to know, how different is that from 0.34? Is that a little different or a lot different? Well, now we've got a ruler. We've got the standard deviation of a normal model as a ruler. As always, the z is just the change. Let's write out the general formula first. It's the p hat, so to change between what you observe minus the center. We're assuming this is a normal model centered on p naught. That's the null hypothesis, that the true population is p naught, and we're just going to get variation around that in the middle, divided by that standard deviation of p hat that we just calculated. Okay, and we can put in the numbers. That's 0.33 minus 0.34 all over 0.0052. Okay, so now let's calculate that. Not too hard. And it's about minus 2, but not quite. Minus 1.923. Okay. So that means that what we've observed as our sample is a little less than 2 standard deviations away from what we think we'd observe if the null hypothesis were true. Okay, so what does that mean? Well, we need to get a p-value. Okay, now let's remember, this is a two-sided test, so we want to figure out what's the probability of being in either tail, high or low, at 1.9 standard deviations away or more. Okay, so it's double the probability of, let's say, z being in the left-hand tail with that critical z value. Okay, so we've got a normal distribution, and we're thinking, okay, what's this? The p without the 2 here. This would give the probability that in a random normal distribution process, I would have a z value less than minus 1.923. I would be to the left of the hump, the middle, the mean, by more than about 2 standard deviations. We double it to make sure we also include the possibility, well, actually, maybe it's more. Okay, so it turns out that I went ahead and used the calculator, just normal CDF. Actually, let me write it down. It's 2 times normal CDF of, I did like minus 100, just some big net number, minus 1.923, and then 0 and 1. And for some reason, the computer's hanging on me. So that's the normal CDF calculation we're going to do. And it's really annoying that the computer is messing up on me. Okay, there we go. 0 and 1. Okay. And that turns out to be, with the 2 included, that turns out to be 0.544. 0.0544. That's crucial. And so that's 5.44%. Okay. So if the null hypothesis were true, if it were still true that 34% of students were the real population, and I just took this sample of 8302 responses and I happened to get 33%, well, that or more extreme difference is going to happen 5.44% of the time. So about 1 out of every 20 samples is going to give me, if the null hypothesis were true, is going to give me a 33% or a 32 or a 31 or a 35 or a 36. So that gives me an idea of just how weird is this if the null hypothesis were true. If this were 0.001%, we would say, gosh, I think the null hypothesis isn't true, because if it is true, this would be an incredibly unlikely event. Well, this isn't super unlikely. Okay, so I would say we fail to reject the null hypothesis at a level of, let's say, 5%. Okay, because this probability is bigger than 5%, because if the null hypothesis were true, this could have happened by random variation a fair number of times. Not often, less than, between like one out of every 18 and 1 out of every 20 times, something like that. But still, that's not a p-value we usually are happy with. Okay, so it really could have just been random. Now, if you wanted to go ahead and have a bigger critical level for the p, you could say, well, we would reject the null hypothesis at a level of 10%, but few people use such big percentages, because it's just getting into like, well, are you really sure this wasn't random? Let's try to be more sure about this. Okay, so I would say we fail to reject the null hypothesis. It's not obvious that there's really any difference here. Okay, and then the last thing is just the significance. Okay, we have not shown that there is a significant difference in attendance between 1996 and 2000. Okay, but we do not assert that there is no difference. That's this very different thing. In other words, we do not say that we have proved the null hypothesis. Okay. For example, suppose that we went back and said, oh, actually there was a bigger survey in 2000 that had 20,000 responses, and it also gave 33%, or maybe it gave 32.8% or something like that. These numbers, in particular the n here and the standard deviation, would change, and I could get more significance out of this result. Okay, so it's very possible that if you just studied it further, you'd discover, yeah, there is a change. Okay, now notice that even if there were a difference, it seems unlikely to be large. Okay, in the sense of real-world significance. There's statistical significance, which is, could this have happened by chance? And then there's, okay, suppose we actually made a bigger sample size and got this p-value much smaller, and we discovered, okay, we really think it did go from 34% to 33%. Are we going to throw up our hands and say education is ruined and these kids are never coming to class? Even if this were a real change to 33 or 32 or 31, it wouldn't be cause for a huge amount of concern, probably. The way we would further explore that is put a confidence interval on it. Let's say we'd say, well, what's the confidence interval we have? Given that we didn't even reject the null hypothesis, there isn't really any need to go to that stage of building a confidence interval for what we think the true new 2000 proportion is, because as far as we know, we don't have any evidence that it's different from the baseline, which was 34%. Okay.